Culham as a fusion lab has been in existence since the 1960s. The huge potential comes from the sort of limitless supplies of fuel. The fuel for fusion reactions are hydrogen and its isotopes, deuterium and tritium. We know it works because if you look out the window in the daytime you see the sun, at night you see the stars. They run on fusion. Fusion's the process that provide the energy for the sun and stars. In the sun, the centre of the sun is something like 15 million degrees C, and that's the temperature's high enough there to overcome the nuclear binding energy, and you actually fuse, hence the name fusion. You fuse the isotopes of hydrogen together to form helium, which gives a huge energy release. Here on Earth it's somewhat more difficult. We can't do things at 15 million degrees C. We have to do them at nearer 200 million degrees C, which gives you some big engineering problems if you try and contain something at 200 million degrees C. And this is done by forming a vacuum vessel and constraining the plasma, which is a collection of ions and electrons formed from your fuels within magnetic fields. And these we bend round into a donut shape, which form the torus or the tokamak. JET is a tokamak hosted here at Culham on behalf of EFTA, and JET from 1983 has been operating to establish the physics basis for the design of future machines. With the growing world population, we need to do something. Obviously we can't keep burning fossil fuels or they'll run out. Fossil fuels are in distinct areas of the globe. The advantage of fusion really is that the fuels are distributed around the world. Deuterium, one of the main fuels, comes from seawater, and lithium, which is widely available around the globe in the Earth's crust or in the sea as well, is one of the other consumables. It's not the fuel. When you have a fusion reaction within the tokamak, it releases a neutron. The neutron comes flying out through the metal structure in collision with the lithium, transfers energy and releases tritium, which is the other fuel which can be recycled back into the machine. There are concerns about, is it safe? Fusion is so hard to get started and so hard to keep running. Pressure at the centre of the plasma during a pulse is still only atmospheric pressure, so if anything goes wrong the machine just turns off, so there won't be any disaster mushroom cloud proportion. If you take the water in a bath full of water and the lithium from a laptop battery, that would supply the energy need for a person for 30 years in a fusion reactor. That's equivalent to something like 40,000 tonnes of coal. You can imagine the environmental impact of burning 40,000 tonnes of coal twice for an average lifetime for every person in the world. The environmental impact from burning an equivalent amount of fuel to produce the energy you need from fusion is virtually zero. There's no carbon emissions. ITER, the International Tokamak Experimental Reactor, is based in Cadarache in France. It's a huge leap in size and complexity as well. We need to get governments on board, get realistic funding into fusion, and then things can happen far more quickly. I think the major disadvantage for fusion is it's not available now, and it's not available now because it's not taken seriously enough. If it's taken seriously by governments and the general public, then it would be an available energy source a lot sooner than it potentially will be. You could argue we box above our weight in Europe in fusion and in the world.